Hey everyone, welcome back. We're going to pick up right where we left off. We had just finished learning about the Hamilton method for apportionment, and we saw that it was a very easy process to use. There wasn't a whole lot of difficulty. It was very straightforward, and it seems to make sense. But as we've seen before with the voting methods and things like that, there tends to be problems with some of these techniques. All right, so there was controversy, a lot of controversy that surrounded Hamilton's method, and it was subjected to these things called paradoxes. And these paradoxes and where Hamilton's method went wrong in history are described here. And there were three separate incidents, one known as the Alabama paradox, another one known as the New States paradox, and then over here, I don't know why that's way over there, was the population paradox, which happened in Virginia in 1900 and 1910. So what I want you to do is I just want you to read through those population paradoxes. I'm not going to go through them in detail in the video, but I want you to read through those in preparation for tomorrow's lesson. Tomorrow what I'm going to do is we're going to take an in-depth look at each of those paradoxes, and I'm going to give you an example on a smaller scale of how those paradoxes occur. So that way you can see the issue with the Hamilton method, and we'll have some nice examples laid out for you so you can see how those work. All right, so for now, I just want you to read through those in your notes, and then tomorrow we will demonstrate each of those paradoxes. So for now, we're going to skip ahead to Jefferson's method. All right, so Thomas Jefferson had a different method for apportionment. After Hamilton's method was vetoed, Jefferson's method was adopted, and it was used in Congress from 1791 through 1842. So this was the first major apportionment method that was used, not the first one that was proposed, but the first one that was actually used in our country. All right, so this is kind of where it all began, and it is actually the first of what we called a modified divisor method. All right, and I'll demonstrate what that means here in just a minute. Now, just like with the Hamilton method, we have a step-by-step here, so you can always read through this just to kind of wrap your mind around the different steps that are involved in Jefferson's method. But instead of reading those to you, I am going to just demonstrate a couple of examples, and you'll see each of these steps in action. Okay, so here we go. Start off with example 3. We're going to go back to Delaware, and instead of apportioning Delaware's representatives to their counties based on Hamilton's method, we're going to use Jefferson's method. All right, now Jefferson's method starts off very much the same. You might remember me yesterday talking about how all of the apportionment methods essentially start off with the same two things. First, we have to find a divisor, which we already know from doing Hamilton's method on this same state was 21,900.82927. And then we need to go through and we need to find the quotas. All right, and the way that we find the quotas is no different. We're going to take the population and or the population of each county, and we're going to divide by our divisor. So the 21,900 ... here, right, with all the decimals. So we'll go through that, and we should get the same quotas that we got before. So we'll have 7.411. And then for Newcastle, we would get 24.587. And then when we find the quota for Sussex, we should get 9.0017. And then we do exactly what Hamilton did. We're going to go to the quotas here. We're going to ignore the decimal parts, and we're going to do an apportionment. So we do 7, 24, and 9. And then we add those up to make sure that we have apportioned all of the representatives here. So when I add those up, we get 40. And we know that 40 is not enough because we need 41, right? So recall what Hamilton would do is he would go back and award the bonus representative to the county that has the highest decimal portion. But what Jefferson decided to do with the bonus representative was to modify the divisor, right? So with the divisor that we had before at 21,900, we didn't apportion enough of the representatives. So Jefferson said, well, let's just artificially lower the divisor. Okay, so instead of 21,900, we're going to try 21,500 and see what happens. All right, so we reapportion or recalculate our quotas based on this modified divisor. So I'm going to take this population from Kent County, and I'm going to divide it by 21,500. And I'm going to do the same thing with the other two counties. and we'll get new quotas. They should be different from before, right? So now the quota in Kent is 7.5488. And again, feel free to check my numbers here. All right, and then we've got 25.0455 for Newcastle, and then for Sussex, we'll have 9.16. So we can see our old quotas, we can see our new quotas, and we see that they do change. And then we just continue on with Hamilton's method, where we ignore the decimal parts here. So we're going to initially apportion 7, 25, and 9. And when I add those up, I now have 41 of my representatives apportioned. So that means we're done. We apportioned 41. All right. So instead of going back and awarding to the highest decimal value, we modify the divisor until that initial apportionment lands exactly on 41. All right. So that's how Jefferson's method works. So in that case, if we look at it, the Hamilton method and the Jefferson method provided for the same exact apportionment, but it happened in different ways. Right. So Hamilton's method and Jefferson's method agree here. They're not always going to. All right, so let's try it again. Let's look at example 4. All right, so we're going back to Rhode Island this time. And recall from our previous example that we had a divisor of 14,034.22667. All right, so we're going to use that same divisor here. We're gonna go through and divide the population by that 14,034. I'll just dot that, and then we would calculate our quotas. So they should be the same quotas that we had from our previous example. So 3.5538, and then 11.839, and then 5.906, and then 44.6528, and then 9.047. And then we would ignore the decimal parts and do our initial apportionment here. So we would get 3, 11, 5, 44, and 9. And when we add those up, we would get 72 representatives apportioned, right? Which we already know that's not enough. We had the same problem when we did the Hamilton method, right? So we've got 3 bonus representatives that we need to get apportioned here. So we're going to lower the divisor. Okay, so we're going to lower the 14,034 to a smaller divisor. We're going to try 13,500. Okay, and we're going to go through and recalculate our quotas. And you start to see why this is a little bit more, I wouldn't say more complex than Hamilton's method, but it's more tedious because we have to keep doing this over and over again with our new divisors. Okay, so I'm going to go through, I'm going to be dividing each population by 13,500 and looking at my new quotas. So here we'll get 3.69 for Bristol. We'll get 12.308 for Kent, 6.1398 for Newport, and then 46.42 for Washington. Right? And then we go through and chop off those decimal parts. So 3, 12, 6, 46, and then for Washington, it's 9.4-ish, so 9 for them. And when I add those up, I think we get 76. So 15, 21, that would be 57, 67, yeah, so 76. And that is too many. There we go. So that's too many. We only have 75 representatives to apportion, but we ended up apportioning 76, so that's too much. So we dropped our divisor a little bit too much, so we need to raise it back up. So we got to do this again, but this time we're going to do it with 13,700. All right, so now I go back, I start over. And this time we're going to be dividing by 13,700 to get our new quotas. So remember what happened there was we dropped it down to 13,500 and then we ended up apportioning too many. So we have to raise it back up because we went too far. Okay, so we're going to go back a little bit closer to our original divisor of 14,034. And when I go through and I divide by this new quota, we get 3.64. We get 12.12. We get 6.05, 45.10, and 9.268. So we got 3, 12, 6, 45, and 9 when we chop off the decimal parts, and if I add those up we get exactly 75 candidates. So this would be our apportionment. 13,700 becomes the divisor that we would use for this particular system. So we see that this works. All right, so just some notes about Jefferson's method. It's tedious. There's no easy way to do it. You might be asking, well, how do I know how far to go when I lower that divisor? There really isn't any way to know. Just pick a nice like a nice clean even number to divide by and start there. If you go too far, raise it back up. If you didn't get enough, keep lowering it. It's really a trial and error method, which is the big drawback of it is that it is tedious, and there's really nothing that can be done about it. Okay. One of the other issues with Thomas Jefferson's method was that it doesn't always follow the quota rule. You might have noticed in our previous with our previous one here, right, our initial apportionment was 44, and when we lowered that divisor for Providence, they jumped up to 46. So the difference between the quota, the original quota that we got, and our final with Jefferson here was almost 2. All right, and that actually violates the quota rule, and it can happen. It's not guaranteed to follow that quota rule, which is an issue. Okay, so Jefferson is not guaranteed to follow this rule. All right, guys. So that's it for now. I just wanted to make sure I demonstrated that Hamilton method. Have a great day. If you have any questions, come on back to the Zoom chat.